have everybody here today. And as ever, we'd like to thank our principal sponsors, BP and Shell, and also Equinor for their support of our public programme. Because without them, we couldn't put on events like this. I know we haven't got great numbers, but hopefully that'll lead to more conversation rather than just a talk, and we can get involved as well. I'm sure it'll be wonderful.
Thank you. Thank you very much. Well, thank you very much, audience, to be here. Today, I wanted to do the event rather than just being like a monologue that you are listening to what I need to say or whatever. I wanted to involve the audience. So you're not coming here to learn, but to work. So, you know, the idea here is that you've got probably something called the labels that are with you. So that one has a couple of suggestions of things, and then you also have a leaflet, this one, that contains a little bit of a work that has been already done. So as we progress with the presentation, you would notice that probably it's not quite easy to just name the machine, because we are meeting two different things in one single piece of hardware. So the idea that we are bringing is what TWEFDA stands for tidal and wave energy from decommissionable assets. So the first thing that we find there is tidal, wave, decommissionable assets. What is it about? You know, what are we doing? Just the title. But then as we go a little bit in depth, understanding the machine that we have brought, a prototype that we can then, after the event, just check a little bit, know what it does, and why is, in my view, so special. This particular machine harnesses at least 3 proven renewable energy resources. So it's like having 3 machines in one piece of hardware. There's no, I mean, we may think, imagine that you've got a hut that has solar panels and a battery. So you've got 2 machines there, right? But they are 2 different machines. One is generating and the other one is storing. This particular machine has the possibility of store energy or generate energy. And that or is extremely important, because imagine that it's 3 a.m. at night, we are all sleeping. There is a great demand, but there's small demand, sorry, of energy, because everyone is sleeping. No one is using that energy. And it's a windy night, you know, all the wind turbines are producing a lot of electricity, but that leads us to curtailment. We need to stop the wind turbines to be producing, because basically we don't need that energy. And, you know, everything will blow up if you continue producing energy. It can be also the case that we've got a battery that is charging when the energy is scarce. So in both cases, we are harming the grid. The way we are addressing that is by switching. So you are now in generation mode. I don't want you to be in generation mode anymore, because we need now storage machine. So you just press a switch, send a command from the grid, and that machine will start in a different generation or storage mode. If you see the leaflet that is here, you can see that there is a hub. Let's see if I've got no. Yeah, well, this particular device, well, this is the hub where all the operations of energy are taking place, and that's the first understanding of the idea. So tidal and wave energy from decommissionable assets, because that particular hub that you can see there is potentially a repurposed asset. You can see there the jacket is repurposable, potentially again, because those guys there have been there for 40 years. So sometimes it's doable, sometimes it's not. But then we've got the jacket, the platform, you've got the pipeline to import, export, potentially hydrogen, and we've got the well to potentially store CO2. So all those things are potentially doable. It depends on the nature of the floor. So CO2 is not always storable in any well. So it could be done, it could not be done. But I'm saying the potential that those things have. And according to the Oil and Gas Technology Center, 30% of the pipelines are repurposable for hydrogen purposes, right? Hydrogen, as you know, is a very tiny molecule that escapes very easily. So it must be very high standards in the pipeline to do that particular work. But we can also import CO2 from the coast, from shore, by using that particular pipeline. So even if there is a little bit of leakage, it doesn't really matter. Well, we need to take into consideration is that not always that CO2 can be stored straight away there. It depends on the nature of the well and so on. And here we can only see one of the devices, but in the leaflet, you've got 6 devices. And 6 devices means that we can be using one in generation mode to supply to the customer. 2 more can be in generation mode, but to supply other devices that can be in storage mode, harnessing that energy that is then kept to be released afterwards. And we can also see there are wind turbines there because this is a very collaborative approach. So basically, the energy does not necessarily need to come from us. It could come from other generators offshore because you've got the hub there, you've got a certain capacity of storage, but once that capacity is met, what are we going to do with excess of energy? So what we can do is use an electrolyzer, because that's an energy hub, and we can start producing hydrogen that we can export to the grid. And I think that's a very interesting opportunity because I want to make you think a little bit about this particular reflection. I am a hydrogen lover. I really love hydrogen. Hydrogen is the molecule that is more abundant in the universe. We should be doing something about that. But right now, we've got a problem with the performance, the overall performance of hydrogen. And slowly but surely, we are creating a market with hydrogen, which in my view is a little bit dangerous because we don't really have the capability of producing all the renewable energy that we need so far. And we are using a massive amount of that energy to produce hydrogen, which again, you know, I really think that we need to address the hydrogen thing because it's an amazing technology. But the way we are doing that is probably discussable at least. Anyway, let's see what's in it for you guys. You're a variety of audience. It's not investors, it's just stakeholders of the same thing. So let's read a little bit that through and we say, my business? Not only, it's also your business. So TWEFDA can potentially reuse old oil and gas platforms. This defers decommissioning costs, which are partially paid by you as the taxpayers and that are measured in billions. I was saying before that there are 2 more revenue streams associated to that, which is that if you've got an asset, you don't need to remanufacture that. And that's money to remanufacture the device, but it is also a huge environmental component. We need to produce a lot of CO2 to create any assets. So there are great benefits on that. And also, if we are deferring the decommissioning process about 20, 30 years, potentially in that time frame, the technology will evolve. And instead of having one single ship dealing with all the decommissioning process, we may have several, or we may have other techniques that make that particular process of decommissioning more profitable. So there are like 3 different revenue streams there. But the energy we consume needs to be produced instantly, and the less resources we use for that, the better to achieve net zero in a cost-effective way. The dual functionality of generation and storage will allow the most appropriate use to be carried out. If there is an excess of power in the grid, our system will swallow the surplus by behaving in storage mode. If there is not enough power in the grid, our system will either release the energy stored or behave in generation mode to tackle the deficit. Just now, too much energy leads to curtailment or to the need to bring storage machine in addition to the generators that are producing the excess to absorb the surplus production. In a deficit situation, we need to burn gas to balance the grid, which is a third machine. And guess what? We as taxpayers all pay for the efficiencies and inefficiencies of the grid. Yes, it is your business. So I wanted to leave it that there, because now I will put a video. At any time, the grid requires either generation or storage, which means that these 2 functionalities are complementary. A wind turbine providing power when required is great, and so is a battery of any kind charging when energy is abundant. However, if the wind turbine produces power on a windy night, when demand is low because everyone is sleeping, or the battery is charged when energy is scarce, their functionalities are counterproductive. It's worth saying that despite all the efforts of the national grid to reduce our bills, we all pay for the efficiencies and inefficiencies of the grid. Summing up, generator and storage devices are welcome if they provide or store energy when it is required, and not just when it is available or abundant. Imagine a single machine that can generate and store energy with outstanding performance, providing the renewable energy we all want, with the capacity to store excess from other generators in the grid, working 24/7 thanks to its dual complementary capabilities, with high capacity to ramp up or down both power absorbed and delivered. Imagine that in one single piece of hardware, we could harness 4 different renewable energy resources. It's like having 4 machines in one. This disruptive concept is called the ES wave and will completely transform the very perception of energy in the world. Curtailment, intermittency, and lack of storage are words that are starting to be part of the past. The ES wave will bring the necessary flexibility we all want, with a tool that will truly help balance the grid by providing what the grid requires at any time. This is a great opportunity because, as mentioned by Andrew Lever in the video report from the Carbon Trust, investing in flexibility is a no-regrets decision worth £16.7 billion per year across all the scenarios analyzed for 2050, just in the UK. The dual functionality of TWEFDA's proposal may help reduce that amount by a significant proportion. And once again, this is taxpayers' savings. It's measured in billions, and only considers the UK. However, finding flexible options to balance the grid in a decarbonized economy are world tasks. You may want to hear that TWEFDA's financial plan forecasts to achieve £1 billion in 5.5 years. Our strategy embeds collaboration. This allows TWEFDA's partners to become experts while our technology is rapidly deployed. Two complementary functionalities, 4 machines in one piece of hardware, multiple business streams, considerable savings for taxpayers, and all in one single project. Interested? Okay, so before I continue, I would love to get some questions for the audience to just wake up a little bit. So, any thoughts, anything that has not been understood very well, anything that you want to recap on?
I'd like to ask, what are the core things that does?
That's great. That's a very good question. Thank you very much. So the device we've got here has the it's called a point absorber. So it's a wave energy converter, and it does that because it harnesses the relative motion between the steady seabed and an oscillating sea surface. So that's one of the machines. This particular machine, you can see that it has a very big cylinder. That very big cylinder is not required for generation mode because it is going to move a couple of meters maximum. So it's so big because it can be used to lift up the entire device, as you were seeing in the video. And by doing that, it's creating a pumped hydro application in the middle of the ocean with no environmental constraints. And on top of that, if the tide is up and the device goes up, when the tide goes down, we've got an extra range to harness, which is the tidal range. And that's another renewable energy resource. So that's the third machine.
Hold on. All right.
The fourth machine, sorry.
So I just want to clarify. So that the act of it going up and down, you generate this, I think you've got some sort of gear system in there, and then produces electricity as you go, you have that movement there. Then you said also like some sort of oscillation device, is that what you said? So there's like, it can charge.
Yeah, well.
On that axis, is that what you mean?
Yeah.
Just trying to confirm.
Yeah, no. The confusing part comes with the functionality. So if it is in generation mode, it's fixed, it doesn't go up, it goes a little bit up and a little bit down with the waves, right? But then it comes to storage mode. And in storage mode, it lifts up about 15 meters above the sea level. That's also a survivability thing because 15 meters means that you need waves of 30 meters in height to start touching the lowest part of the device. So it's a survivability issue. But at the same time, a mass at a certain height is gravitational energy. So once we take the device down, that gravitational energy is converted into electricity. So at that particular moment, it's not moving at all. It's just here, right? And here's the surface.
Okay, so I've got a few questions off the back there.
There you go for it.
Right,
Go for it, thank you.
So, okay, so the energy generation is one. It's like how much energy can you produce during that action, right? So there's like, let's go that question. Should be hopefully a quick one. And then it's like, well, when it's in storage mode, is it just the potential energy of it falling? Is that, or is there some sort of battery capacity there?
No.
And I suppose another thing is, how does it get 15 meters down in the first place? Because we have to use some energy to get that.
Yeah, exactly. And that's precisely the key point, because at 3 a.m., I was mentioning in the video, everyone is sleeping. So that energy is not really required. And if you can lift up the device, which is using a pump, is using energy from the grid, or using another device, because this is effectively a pump, right? So you can use one of these pumps to lift up another. But let's say that we are absorbing energy from the grid. So we've got here the ramp up and down flexibility, because the device can be completely empty and is then lifted up. As a result of that, there is small mass. You can lift up one device or the 6 of them together. There are a couple of ballast tanks in this particular device that can be either full of water. If it is lifted up as an empty device, then you can start pumping water to the tanks and gaining mass and therefore potential energy. But that way you are ramping up or down the power absorbed or the power delivered. If you think that it's 3 a.m. and there's a huge demand for someone who swallows all that excess of power, you can lift up the 6 devices together with all the ballast tanks full of water, and that will absorb a huge amount of electricity, as you may guess. But you can also lift up one single device with a set of 6 pumps that will go very quickly up, but it will absorb little energy. So we can play with the amount of energy that we need to absorb, and that will be matching the grid's needs, which is precisely what we should do. Just you say, well, it is going to absorb a huge amount of power, but that's the idea, because there is a huge amount of power available that nobody else is using. And once we've got the 6 devices up and fully charged, we can start, because we've got a hub there that has a huge amount of energy, because it's probably even connected with other offshore generators. So, because there's no need for the electricity that is being produced there, you can start hydrogen production. And I believe that's the strategy, because you don't really need that energy. That's why producing hydrogen is marvelous. The problem is when we are producing hydrogen and we are needing that electricity to serve the grid, because we are, we've got scarce energy available, and we are using that to produce hydrogen, which is something that was not a demand a few years ago. And well, let's keep that way. So I spoke about 3 machines. There is a 4th machine that I want you guys to see that with me, which happens with, let me see if I've got the particular thing here. So here you can see a preliminary hydrodynamic analysis that we performed with what we undertook with a reputed consultancy called TWEFDA. So the idea for this particular approach is simply magic, in my view. And this is, we don't have the testing, so we didn't really check this in real life, but we did that with OrcaFlex, which is a recognized piece of software. And what happens there is that the same device in 2 different conditions, one opening and closing a ballast tank, produced 2 very, very, very different outcomes. So I need to explain a little bit this particular one. So the approach that we took was basically the device goes up with a small mass and goes down with a big mass. How can you do that? If you throw away one object, it goes up and it's exactly the same one that goes down. Then there's no violation of energy. We are putting a certain amount of energy in the system, and it goes down exactly with the same amount. But what would it happen if you've got an open communication with the ocean, and then as the device rises to the highest position, you close that tank? So you close that tank, it was always full of water, but now the tank closes and traps all the water that is within. So that tank is called DCT, it's a dynamic compensation tank. And this was the outcome. It's not that I am saying I think it could be good or not. It's a normal device without dynamic compensation tank, so the device is completely closed at all times, will deliver about 75 kilowatts. And the device using the dynamic compensation tank will deliver 190 kilowatts. So it's not 75 to 80, it's 75 to 190, is even more than twice, without any optimization whatsoever. It was just a preliminary hydrodynamic analysis. But then let's go a little bit in more detail, because the wave power in that case was 100 kilowatts. Can anyone explain to me how is that possible? Do you have an idea how out of 100 kilowatt you can produce 190? What is necessary for that to happen? How can that happen? Well, you probably know about a heat pump. So a heat pump utilizes electricity to move a fluid, but in reality, it's bringing heat from outside to inside. So what we are pumping is effectively heat, and the heat is in the atmosphere. It's a different resource. So we are effectively bringing heat from outside to inside. So that's why we can achieve 300, 500% performance. It's not true, because there are two flows of energy coming in. In this case, we have called that the wave changing energy, because it goes up with a certain mass. So when you formulate the lowest and the highest position, you can compare those two. But then when the tank closes and doubles or triples the weight of the entire device, that energy is then released by double or 3 times the amount. Did you get that? Do you know what I'm talking about?
So, just to confirm, what I think you're saying is, it sits in the water.
Yeah.
Right? It goes, it's wall to water around, with the inside as well.
Yeah.
The waves rise.
Yeah.
And it keeps the water inside, and as the wave drops, it will then drop. And then therefore you're using the extra weight of an extra head.
Exactly, an extra weight along a stroke is a resource of energy as well.
Is that what it was?
Yeah, exactly. But the key point here, you will see this one once you come closer. But this tank basically rotates and closes or opens. It's very high. This rotation allows the water to be trapped or untrapped. The idea here is that when we are in open communication with the ocean, the water doesn't weigh. It doesn't weigh because it belongs to the ocean. But once we trap the water, it weighs because it belongs to the system. So that particular water that happened to be in the right position, in the right moment, we're using that weight along the stroke to produce a renewable energy source that has not been explored before. That's my perception. I've only have a preliminary hydrodynamic analysis. I'm surrounded by very clever people, and I would like you to tell me, what do you think about this? I mean, that was one of the ideas of coming here, just to get some feedback of what you guys think, and also to try and summarize everything I've said so far, to put a title. So if someone asks me, what are you doing? What should I say? I think speaking about tidal, wave, decommissionable assets, wave-changing energies, 4 machines in one single device. I've been speaking about dual functionalities, generation and storage in the same tool. And there are a few more things, because the thing is that when we speak about a pumped hydro application in the middle of the ocean, this is said very quickly, but when you try to go a little bit into detail, you realize that a pumped hydro application is a 1 billion project. We need to bore a tunnel through a mountain and connect to different reservoirs that are at different heights. That has a huge environmental consideration. All the activists will go straight to the street and say, stop that, you can't do that. Usually, it's a project of 15 years, where 10 years is just to be consented, because it has a huge environmental impact. Imagine if we can do that in nowhere, just in the middle of the ocean, with no environmental constraints, and because that particular device is floating or is staying in the middle of the ocean, it's like an island for birds to rest or even breed. So instead of harming the environment a lot, we are providing a resource for the first time in our lives. We always do something bad with the environment, but anyway. I don't know what you guys think about that, but that's a great value proposition. That single thing, without proving anything else, is sufficient to have a huge business case, because we really need storage in massive amounts. And that means that this brings another conversation that is required, but that's too much for today. The main thing is that I would like you to group, because we are not that many. I think we can go to 5 and 6. There's 6 there, up to you, and 5 here, up to you. You can rearrange the groups if you want, but I would love if you've got here in this leaflet one statement and a few value propositions. You already heard what I said, and the intention for this particular game or exercise is to try and find an alternative text for that. We also have, I will put that there, but you got this printed with you. So there is like a big statement. It says, developing a hybrid machine, the ES wave, which is capable of harnessing unprecedented levels of energy from waves, and also to store large amounts of energy, creating a pumped hydro application in the middle of the ocean with no environmental constraints and with great efficiency, thanks to the use of the tidal range. That doesn't happen in a normal pumped application. The reservoirs are exactly at the same level at any time, but here we can play with the tidal range to get even more. So 4 machines in one, working for 24/7 to provide what the grid requires, reducing its inefficiencies and lowering the costs for the taxpayers. So that's a large definition. Usually, you don't have so much time to speak about the device. But then we have another one, which is hybrid wave energy converter with outstanding performance and green storage for the grid, also harnessing the tidal range, all in an offshore collaborative scheme, working 24/7 for a decarbonized economy. So-
A question, but,
Yeah.
you got any numbers?
Yeah, I do have numbers. So
What I mean by that is like the cost. And so, for example, I mean, that's interesting that there was a difference in those numbers there. You said it was 140 kilowatt. Is that what you said there?
no, well, no.
108 kilowatt?
This particular one was it's a preliminary hydrodynamic analysis, and the
Based on
device
size, and you like the size? You know,
it's a
20,000.
5 meters and is done with a 20 kilowatts per meter scenario. So it's power absorbed in regular waves with 1 meter amplitude and 5-second period. If you know a little bit about the theory of waves, that probably you do, is 2 meters in height, 1 meter amplitude is 2 meters in height. That will be the height to the square, so it's 4 and times 5, which is the period, is the power in kilowatts per meter. So it will be 20 kilowatts per meter. The device in this particular drawing is 5 meters in diameter. So it's 100 kilowatts, the maximum that any chart should show. But it's not, it's showing 190. And that's why this particular example is a clear evidence that something must happen. 75 kilowatts out of 100 is a great performance. 75% performance is great. But the 190 is unrealistic unless there is something else. There has to be something else. That's my perception. It needs to be proven. And in fact, when you think about it, if it goes from one particular part to another, you can think in the potential energy to achieve that. Well, let's put it in a different way, because it will be, I think, better understood. So you've got a floating device. It's not linked to the ocean at all. It's just simply floating, right? And you've got this particular tank that I was speaking about, this dynamic compensation tank. So you've got a crane, and the crane is lifting up the device, right? But the tank is open. And because the tank is open, the crane only needs to lift up the mass of the device, right? Because the water will leave. So we monitor the energy that we have used to lift up the device. We put that is E1. And then we come back to where we were. The tank is still open, but now it's floating. It's exactly where it was before. But now we will close the tank. The tank is flooded. There is water inside. So we close the tank. We use the same crane to lift up the device once again. What would happen? Would we need E1 to lift up the device? Clearly not. The water has doubled the weight of the device, and therefore you need twice the energy that you used at the beginning to lift up the device. So clearly, when the mass changes, well, this is not rocket science, it's basic. I think it's a way of graphically seeing what is happening here.
I've got a proposed cost of how much that would be. Like, for example, if an example prototype, imagine the cost would be the main factor, right? Because it's throwing things offshore, and then you've got to make sure it's strong enough to stay in the ground, you go lay cables. Or you put it next to a facility that's already got something. You can test that against the harbor, for example.
Yeah, well,
So
definitely.
you use a prototype. In fact, I think the best one is probably the number 4.
Yeah,
Because the hydro pumping system, you can just pump it up a hill.
Yeah.
And you could just put it down the way. That's not new. But that's interesting. I think that's probably if you convince somebody to stick down their rig or on a turbine or something on the jacket.
Yeah, people usually want to see that particular prototype tested. So we really need to test that one, and that's the next stage. I think we are now communicating with way more clarity and also with confidence, because we've got a PCT on this. So it's a patent pending, but it is at the international level. So we've got some, and this preliminary hydrodynamic analysis is also very, very compelling, because it's not me with a few calculations and a spreadsheet or whatever, saying I think. No, I don't think. We've done study, and we at least the study, because we didn't prove that in the water, and that's extremely important, guys. I totally agree with that. But if you think about it, probably the fourth machine needs clearly to be proven. But what about the other three? You know, creating a pumped hydro application, that's, you know, you've got cranes and you've got lifts that operate with hydraulics. And we know hydraulics from the 13th century. So to me, there's no doubt that when you make an appropriate model, well-done model, that will work, no doubt. That's my perception, right? You know, if I fall under my words, I'm sorry, but I totally believe that that particular machine does not need to be proven. We will prove it, but it's clearly something that will work. The point absorber machine is another thing that we've got hundreds of point absorbers already in the market. Why should it not work? It's probably you can say, well, probably the cylinder needs to be smaller, the weight needs to be bigger, whatever we can say, that's fine. So I'm not saying that I will test it and it will work straight away, probably not. We need to do calculations, we need to do more engineering things to make sure that that will work once we make it. But it's clear that it will. The tidal range is what to say about the tidal range. We all know that the tidal range is there. So the weight changing energy is the only thing that we did a preliminary hydrodynamic analysis, just a study. And I appreciate that this needs to be proven in real environment. No doubt, to me, you know, the four of them needs to be proven in real environment. But that fourth machine is the only one I've got certain doubts. And not that many, because, you know, we now have the preliminary hydrodynamic study, and also it makes sense, because if it goes from one point to another, you can compare energy in the two places and make calculations. But when it goes down, it's a different system, because energy doesn't change in an isolated system. So if we have a system where the mass changes, that's nothing to do with the law of conservation of energy. The law of conservation of energy says that in an isolated system, the energy remains constant. That's not an isolated system where you've got a change of mass. But anyway, that's my perception, and you know, I'm very happy to discuss that with you guys if you want me to. I would like to ask you now, unless you've got another question that I'm extremely happy to answer if I can. What you were mentioning before about numbers. So I don't know how much it costs. I still don't know that. Don't have that. I did some studies, but that's extremely complex for where I am right now. There are many numbers that need to be taken into consideration, and I've got other studies, but they don't have that scope for now. I still need some money to do that properly. But what I can tell you is that our forecast is that in generation mode, that machine will generate about 5 megawatts of power. 5 megawatts is a huge amount of energy. That's our forecast. Yes, please?
That is 5 megawatts for the device that is 5 meters in diameter.
No. It's 70 meters in diameter. 70.
70 meters in diameter.
70 feet. And that brings another discussion, but yeah, it's big. It's not huge, because wind turbines are now about 350 meters in height for 20 megawatts.
But it wouldn't even work, because the distance between the waves would just cancel out. If we have the maximum width that you'd be able to do that for wave technology, and it would just be a big disc in the ocean. We wouldn't do anything. And how would you be able to have a central piece down here with smashed?
Which one? The hub, you mean?
Central, have you got multiple pieces? That's, okay. Well, let's just leave that comment for now.
No, I'm
Like,
happy.
the size, right? There's a bunch of questions, I suppose.
Yeah.
Sorry, I was sort of hijacking you.
That's all right.
No. Well, the thing is that the first numbers we considered to do the studies came from remember the name of the university? Well, Highland. Thank you. Highlands and Islands. So they gave us a profile for the North Sea, and we were talking about 100 to 300 meters in wavelength, and periods between 5 and 15 seconds. I remember. It's just remembering by heart. I don't have the data in front of me, but it was 100 to 300 for sure, and almost sure 5 to 15 seconds. When you go, I think I knew your face. I think you're a developer, are you? No.
Not at all.
Okay. I think, well, it rings a bell. your face. But anyway, the main thing is that if we've got between 100 and 300 meters, here, when we talk about generation, usually the smaller, the better. So more or less 5 meters in diameter should be what Wave Energy Scotland says that is the highest performance. So there are many studies. Why are we saying 70 meters in diameter when 5 meters should be the ideal weight? Well, in this particular patent, we are bringing 3 weight changing mechanisms. So I've been speaking about the DCT, but there are 2 more, because that cylinder gets full of water or liquid, which changes the weight of the device. But there is also a static compensation tank that adapts the weight of the device. And this is extremely interesting because the way it reciprocates, it goes up and down, depends on the mass and the nature of the waves. So basically, if you do a very light device, that means that goes up quickly and easily. But when it goes down, it doesn't release any energy because it doesn't weigh. So if we do a device that is really light as possible, and that is what has never been tested, as light as possible, we can increase the weight by putting water. We can use a ballast tank to adapt the mass for the sea conditions. That's a very interesting thing because, again, the device will weigh what we want it to weigh. So, but by saying that, what I mean is that probably in generation mode is 5 meters for a certain weight that goes up and down and is made of steel that is very heavy. We've got composites that are a 20th, is a 5th of that weight is for composites. So potentially we can make it bigger. But there is also another component which is way more important, and it's the storage component. So the bigger the device, the better in terms of storage. So we can sacrifice a little bit the generation part to give more relevance to the storage part. And in the storage part, if it was 300 meters in diameter, it will work perfectly well. So it will. I can discuss that.
I just don't think of it. Like, not even a little bit, we just think it would just be a floating thing in the ocean.
With 70 meters.
Smaller ones.
Well, probably, I don't want to discuss that because in reality, where we are right now, we didn't do all the computer work that is required. You need ANSYS, you need Orcaflex, you need engineers, you need many things, premises, and work that thoroughly. Every single piece of the hardware we are presenting here should be thoroughly considered before we say something about that. I don't have the software. I don't have the particular expertise that is required to do that, but I think this is absolutely lovely. And on top of that, we've got Core Power Ocean, that is a developer. They are starting to be commercial, and they are, for instance, not using the way changing energy. That potentially could be good for them, potentially because the way they work right now is not doable. But the main thing is that that project is viable and is using this 75 kilowatts, and it's viable. And it doesn't have other considerations about the mass. It doesn't repurpose other assets. There are not other revenue streams. Probably I'm wrong, but this is a case that we have to study. You know, it's not saying that it's for sure true. It is for sure 70 meters. No, nothing of that is definitely a number. It's the numbers that we have been dealing with, because at the stage we are, we need to do assumptions, and those assumptions are supported by a great belief. It's not just to say it's bigger. Why? You know, if it was smaller, you need to get as much power per unit of mass as it is possible. So probably with smaller devices, you've got a bigger performance on that. But at the same time, again, the storage component to me is crucial, because even if it was just a storage device and it will not generate at all, that's an excellent value proposition. Yes?
Yeah, I find this, I know a little bit about this device because I spoke to Javier before, but I find this discussion fascinating. But if there was a challenge with having a 70-meter system, so I think your concept then, as you showed in the diagram we've got here, is one oil rig, decommissioned oil rig,
yeah,
surrounded by 6 70-meter energy systems.
Yeah.
And if it turns out that 70 meters is the wrong size and 10 meters might be better, what's wrong with having
nothing?
100 around it?
Well, yeah, you can do that. Well, the thing is that it comes a little bit, it can be studied, no doubt, but well, the design we did for the hub so far is considering 6 because they cooperate better. So there are manifolds, you know, just dealing with all the flows that are coming in and out. Some energy is diverted for other devices to lift up, not just with waves, but with also pressure that has been created by other devices. So when you put many devices, that is not doable. It's perfectly doable and probably will work even better. But we need to investigate that. You know, we need to, because imagine the number of pipes in the hub. So we need to have at least 2 pipes, one going there and one coming back per device. So 12 pipes, and these will be big pipes. So all that coming up and 80 pipes is a lot. But probably if they are smaller, then the pipes will be smaller and they can be all together there. We need to investigate this. It's no, you know, I totally appreciate it's not 6. 6 is what is drawn, is what I believe is a right number. But yeah, we need to investigate that.
I just want to check a test. I said, if you were to do a dry run, right? So like literally dry, you had a disc like that, right?
Mm-hmm.
And then you could fill it up with water, right? So you use the pump system,
Yeah.
the alternative system. So then you could measure how much energy it took for you to pump that up to there.
Yeah.
And then when it comes down, you just test how much energy you produce on the way down.
Yeah.
And then you see what the difference is.
Yeah, absolutely. I mean that will be the case of more or less a pumped hydro application. We've got usually performances between 70 and 80% in terms of storing energy in a pumped hydro application. In our case, there are places in the world where the tidal range is 16 meters in height. So we go to the coast of Canada.
Just want to stick on that question just for a second, on the specific pump application.
Yeah.
They're coming up. So you know how much energy you're using to create that, because that's what you have to do during the one of the situations that we mentioned, and then you'll get the energy when it comes down.
Mm-hmm.
So have you done that test?
Yeah, I've done that test with many other considerations, because again, we can ramp up or down the energy absorbed and the energy delivered. So I was mentioning before, was the tank full of water before I started? The 2 tanks full of water before I started, was it one? Was it completely empty? So we can really ramp up a lot, and playing with the entire system requires creating a market, because someone will need to make a decision on whether ES Wave 1 will be in generation mode or storage mode, and what about ES2? So when imagine you've got a business, so there is someone dealing with wind turbines. What are the decisions to be made? Generating, or just doing some maintenance or whatever, stopping generation for doing any kind of work to make sure that everything goes well. That's not the case here. Here we've got generation or storage. So if someone cares about generating, that's not the thing that they need to consider, because probably storage in this particular minute is more interesting than generating. So because you have the dual ability, which one are you going to use? Then, are you going to start producing hydrogen? That's another decision to make. Are you going to deal with CO2? Are you going to use that energy for anything else? So all those questions come together to make a decision on what to do. And that's so far not a problem in the industry.
Thank you very much.
Thank you. Well, what's the time now? It's 7:30. Anything else, guys? I think I wanted to put you in groups and try to come with a statement, but is that something that you fancy to do, or no, not really? Just a cup of tea or something, making it a little bit better. Well, we've been for an hour here. I think is enough. I believe. But if you've got some other question, or otherwise we will wrap up here. Wrapping up. Well, let's do that. So Jenny, do you want to conclude the session?
I'm sure that was very interesting. Lots of good questions and conversation and debate. That was really interesting. If you do have any questions, you can just drop me an email, or I can pass it on to Javier. Not a problem. Thank you all for